Hello, geometry students. In this lesson, we're going to talk specifically about similar triangles. We've been talking about similar polygons in general, but today we're going to focus in on just triangles. And I want you to think back to last semester when we talked about congruent triangles. And you might remember that we proved that two triangles were congruent first by using the definition, showing that all sides were congruent and all angles were congruent. And then we learned some shortcuts like side, 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 and side, angle, side. Well, the same thing is going to be true today for similar triangles. We could show that two triangles were congruent by using the definition. In other words, showing that all three pairs of angles were congruent and all three pairs of corresponding sides are proportional. Or we could use some shortcuts. So we're going to learn some shortcuts today for guaranteeing that two triangles are similar instead of using the definition. So our first shortcut we call the angle-angle similarity postulate, which says the following. If two angles of one triangle are congruent to two angles of another triangle, then that's enough to guarantee that those triangles are similar. We don't have to worry about showing that the third angles are congruent, although we already know that the third angles are congruent. We have a third angles congruence theorem, but we don't need to show that corresponding sides are proportional. Just two angles being congruent is enough to guarantee that two triangles are similar. So if you look at these two triangles, triangle ABC and triangle FGH, you can see that there are two pairs of angles marked congruent, so that's enough to guarantee that triangle ABC is similar to, now when you name this second triangle, make sure that corresponding parts match up. A should correspond to F, and B should correspond to G, and then angle C should correspond to angle H. All right? So let's look at a couple of examples. Are these triangles similar? If so, write a similarity statement. So if we can find two pairs of corresponding angles congruent, that's going to be enough to guarantee. So right now I can see one pair of angles congruent. This 56 or 57 degree angle is congruent to that 57 degree angle. So I think what we're going to have to do is find these missing angles to find out if we have a second pair of congruent angles. Well, because these angles total 180, we can find this missing angle. Angle K turns out to be 75 degrees, okay? And then in the other triangle, the rest of the 180 degrees would be 48 degrees. Okay, so once I have those angles labeled, I see that there's a second pair of angles congruent. The 48 degree angles are congruent, so that's enough to guarantee the triangles are similar. So let's write a similarity statement. We're going to say that triangle LJK, L has one arc, so that would correspond to M, is similar to triangle M, and then let's see, J with two arcs would correspond to Q with two arcs, and then K with no arcs at all would correspond to P. Okay? Now if we look at this second example, it's going to be pretty easy to show that this smaller triangle is similar to this bigger one, because first of all we have some parallel lines and transversals, so I can go ahead and mark some alternate interior angles congruent. Okay, here would be a second pair of alternate interior angles congruent using the other transversal, and then we can even go so far to say we have a pair of vertical angles, so we can easily find two pairs of angles congruent. So that's enough to guarantee that triangle XRS is similar to triangle. Now X with two arcs would correspond to T with two arcs, and then R in the first triangle with one arc would correspond to W, and then S in the first triangle corresponds to S in the second triangle. Okay, now this next example, what you need to envision is a smaller triangle laying right on top of a larger triangle, okay? So maybe I can shade in one of those triangles. I'll shade this one yellow. So if you can imagine this yellow triangle that's lying on top of the white triangle, we can see that we have a couple of pairs of sides that are parallel, so we've got some corresponding angles congruent. So for example, this angle is congruent to that angle. This angle is congruent to this angle, because when parallel lines are cut by a transversal, corresponding angles are going to be congruent. That's true in both cases. And that's enough to prove that the triangles are similar, but I just wanted to point out that in addition to that, since the yellow triangle is lying right on top of the the white triangle, they share this angle L. So we only needed two pairs of angles congruent, but I wanted you to show you how easy it would have been to find any two pairs of angles. So we're going to say that triangle LPQ in the yellow triangle is congruent to the big triangle underneath it, and that would be triangle LJK. So triangle LJK. So now let's look at a second shortcut for guaranteeing that two triangles are similar. And this one is called the side-side-side similarity theorem. And it says if the corresponding side lengths of two triangles are proportional, remember that definition of similar triangles, corresponding angles are congruent, but corresponding sides are proportional. Okay, if all three pairs of corresponding sides are proportional, that's enough to guarantee that the triangles are similar, okay? Whoops, similar, there you go. Okay, so for example, and I know you don't have colors in your notes, but if you look here at this, if it were true that the ratio of this green side to this green side, and again, I'm going to write some proportions, and there would be many right ways to write that. If the ratio of JL to QM is equal to the ratio of the red sides, that would be JK to MP. And if that is equal to the ratio of the blue sides, which would be LK to QP, okay, if the ratio of these measures are all equal, that's enough to guarantee that those two triangles are similar. So we could say that the bigger triangle, triangle JKL, would be, oops, I almost said congruent. We're not talking about congruency here, we're talking about similarity. Triangle JKL would be similar to triangle MPQ, okay? And then we have a third shortcut for guaranteeing that two triangles are similar, and it's called the side angle side similarity theorem, okay? Not to be confused, don't confuse these with our congruence postulates, those were. But these theorems, this says if we have three pairs of corresponding sides proportional, then the triangles are similar. This is going to say if we have if the lengths of two sides of one triangle are proportional, not congruent, but are proportional to the lengths of two corresponding sides of another triangle, and those included angles are congruent, then that is enough to guarantee that the triangles are similar. Okay, so if we take a look at this example, if it were true that the red sides and the blue sides were proportional, in other words, remember proportional means equal ratios. So if the ratio of RS to XY were equal to the ratio of ST to YZ, and if it were in addition to that, if we had those two pairs of corresponding sides proportional, and in addition to that, if the included angles are congruent, so if it were true that angle S were congruent to angle Y, that would be enough to guarantee that the two triangles are congruent. The triangle RST, oops, that's an S, RST is similar to triangle XYZ. So let's take a look at some examples like you will see in your homework. The directions say determine if the triangles are similar. If they are, provide a reason. So that reason will either be, maybe make a little list. The reason's either going to be angle, angle, side, 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 or side, angle, side. Okay. So if they are, provide a reason, then write a similarity statement. So as you look at these two triangles, let me just make sure you know what we're looking at. So we're going to look at this yellow triangle. We're going to see if it is similar to this blue triangle, okay? So as you look at what we're given, we do know that there's maybe a couple ways we could go about this. There are a pair of angles that are congruent. We have a pair of vertical angles, but we're also given the measures of all three sides. So we could either test out to see if these two triangles are congruent by side, 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 or side, angle, side. Either way would be fine. I think I'm just going to go ahead and test for side, side, side. So the way I'll do that is I'm going to take the ratio of the shortest side in the yellow triangle, which would be 5, to the shortest side in the big triangle, which is 12.5. So I'm going to write that ratio, 5 to 12.5. Let's see, need to where I can squeeze this in. So the ratio of 5 to 12.5. Okay. Now we're going to compare that to the ratio of the middle measures. So the middle measure, the second largest one in the yellow triangle is 6. The second largest one in the blue triangle is 15. So let's take that ratio of 6 to 15. So that ratio of 6 to 15, and then I'm going to compare that to the ratio of the largest sides, so that would be 8 to 20. 8 to 20. So now we can see if these ratios are all the same. We can reduce them. This first one, this 5 over 12.5, I'm going to go ahead and multiply the top and the bottom by 10, and let's just call that 50 over 125. Now, if we reduce that, there'd be a common factor of 25. That's going to reduce to 2/5, okay? This triangle, this ratio, there's a common factor of 3, so if I divide a 3 out of the top and the bottom, that will reduce to 2/5. And then also, the third one, there's a common factor of 4. If we divide that common factor of 4, that's going to reduce to 2/5. So we can see they all reduce to 2/5. That means that corresponding sides are proportional. So we can say, yes, these two triangles are similar. The reason that we used it was side, side, side similarity. You also could have used side, 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 angle, side. That would have worked also. But the last thing we need to do is write our congruent statement. So we can say that triangle PQR, now PQ is the middle size side and QR is the smallest side. So when I name this blue triangle, I'm going to take middle side to small side. So I'm going to call it triangle STR, like that. Okay, and then example B, again, we have a smaller triangle that's laying on top of a larger triangle, okay? So I'm going to just highlight a little bit. I'm going to highlight this smaller triangle. I'm just going to outline it in yellow. And the larger triangle I'm going to outline in blue, okay? So you can see that since the smaller yellow triangle is laying right on top of the larger big blue triangle, that they share an angle. So I'm going to go ahead and mark that angle congruent to itself. And now we're going to show that the two sides that form that angle in each triangle, that they are proportional. So what I'm going to do is I'm going to take a ratio of a side of the yellow triangle to the side of the blue triangle. The side of the yellow triangle is 8. The side of the blue triangle, we can use that segment addition postulate and add 8 and 4 to get 12. So I'm going to look at the ratio of 8 to 12, and then I'm going to compare that to the ratio of 10 to 15. Again, 10 is the side of the yellow triangle, 15 is the side of the blue triangle. So compare that to 10 to 15. So those two sides are proportional if these two ratios are equal. So we can check to see if they're equal a couple of ways. You could reduce each one and you should get the same ratio when you reduce, or you could cross multiply. If we cross multiply, we'd get 120 both times. So we do know that those sides are proportional. So that's enough to guarantee that the two triangles are similar by side angle side. Okay, and so we'll write our similarity statement. We'll call the yellow triangle, if I call it I guess it's already named for us. We'll call it AEF. So that would be similar to the blue triangle, ACB. Okay, in the next example, we can see the information we're given. We're given all three sides of both triangles, so we're going to use side, side, side similarity to see if these triangles are similar. So let's just take, write a ratio of, let's start with the smallest side of each triangle. So the smallest side of this triangle is 8. The smallest side of the second triangle is 6. So I'm going to take that ratio of 8 to 6. I'm just going to go ahead and reduce that. Common factor 2, that reduces to 4/3, okay? Then let's compare the middle sides. So that would be 12 to 9. And if I reduce that ratio, 12 to 9, there's a common factor of 3, so that would reduce to 4/3. And then if we take the ratio of the largest sides, that would be 16 to 12. So 16 to 12, if we divide out that common factor of 4, also reduces to 4/3. So we can see that all three ratios reduce to 4/3, meaning all three sides are proportional. So we can say, yes, the two triangles are similar by side, side, side. And then let's finish the similarity statement. If we call the first triangle JK, let's see, JLK, that would be, let's see, medium side and then small side. So if I name the second one like that, we would say medium side to small side, so that would be QMP. QMP, all right? And then in this last example, we see that there's a pair of vertical angles, so we know that they are congruent. Let me go ahead and mark those congruent, okay? And then as I look at these sides, if I compare, let me grab a highlighter. If I compare this yellow side to this yellow side, 10 to 20 reduces to 1/2. If I compare this side to this side, 11 to 22 reduces to 1/2. So I can see that these corresponding sides are proportional, and the included angle is congruent, so that's enough to guarantee that the two triangles are similar by side angle side, okay? And then we can, sorry, there we go. And then we can finish our similarity statement. Triangle TZW, so that's a side that isn't highlighted to the blue, then we would call this one YXW, not highlighted side to the blue side. So YXW. YXW. All right, so you'll see some problems like that in your homework. But I want to finish this page off with just some properties of similarity. And remember, we studied the reflexive, symmetric, and transitive properties as they related to equality. Then we talked about those same properties as they related to congruence. So now we're going to talk about these properties as they relate to similarity. The reflexive property of similarity just says that every shape is similar to itself, okay? The symmetric property of similarity says if a first shape is similar to a second one, then we can turn that around and say the second shape is similar to the first. And then the transitive property always involves three things. So the transitive property of similarity would say if a first shape is similar to a second shape and that second shape is similar to the third, then we can say the first shape is similar to the third shape. Okay, so let's see if we can now solve some problems involving similar triangles. The directions say find each measure. So on this first one, we're asked to find BE, which is X, and then we need to find AE, which is Y, okay? So what I'm going to do is see if I can help you visualize a smaller triangle lying on top of a bigger triangle that would be similar. So I'm going to outline, let's see, the smaller triangle I'm going to outline in yellow, and then the larger triangle I'm going to outline in blue, okay? So let's see if we can first write a proportion to find X. So what I'm going to do is I'm going to use, let's do this. Let's take the ratio of X to the corresponding side in the blue triangle. X would correspond to 3.5. So I'm going to say X to 3.5 is equal to the ratio of two corresponding sides. Let's compare, how about 3 in the yellow triangle to 5 in the blue triangle? So X to 3.5 is equal to 3/5, okay? So I notice in both ratios I took a smaller side to a bigger side, a side of the smaller triangle to the bigger. So that's equal to 3/5. We'll cross multiply then and get 5x is equal to, let's see, 3 times 3.5 is going to be 10.5. So we'll divide both sides by 5, and x turns out to be 2.1. So AE is 2.1. Okay, so now let's see if we can find y. So again, we're going to write a proportion involving y. So this time, let's take the ratio of a side of the yellow to the corresponding side of the blue. This side of the yellow triangle is y. The corresponding side in the blue triangle is this whole thing. So use your segment addition postulate, and that would be y plus 3. So in other words, we're going to take the ratio of y to y plus 3. So y to y plus 3 is equal to the ratio of, let's go ahead and use that comparison of 3 to 5 again. Notice y to y plus 3 takes a yellow side to a blue side. That's equal to 3 to 5. Okay? Now, when you cross multiply in this proportion, remember if you have a binomial, you might want to put parentheses so you remember to distribute when we cross multiply. So we're going to get 5y, oops, 5y is equal to 3y plus 9. So that means 2y is equal to 9 and y is equal to 4.5 or 9 halves. Okay, so that is oh, did I get this backwards? I'm so sorry if I confuse you. X is BE. We were asked to find BE, so let me fix that. This is supposed to say BE. Sorry about that. So now we know what AE is. AE is 9 halves, or of course you could call that 4.5. So now let's take a look at letter B, and again I want you to picture a smaller triangle laying on top of a bigger triangle. So I'm going to outline the smaller triangle in yellow and outline the bigger triangle in blue. Okay, these two triangles would be similar. We'd be able to justify that easily with angle similarity. So why don't we do this? Why don't we take a side of the yellow triangle to the corresponding side of the big triangle and set that equal to this side of the yellow triangle to the corresponding side of the big triangle. So let's first of all write an expression for the side of the blue triangle. Well, if you use your segment addition postulate, that would be 5 plus x. So we're going to call that side 5 plus x. And then again, let's see, this side of the blue triangle, that would be 6 plus 3.5. By the way, 6 plus 3 3/5. 3 3/5 is the same thing as 3.6. 3/5 is the same thing as 6/10. So this would be 3.6. So I'm going to call this whole side 6 plus 3.6, which would be 9.6. Okay? So now let's write our proportion. So I'm going to take the ratio of 5 to 5 plus x. Again, that was the side of the yellow to the corresponding side of the big is equal to, or the blue triangle, and that's equal to 6, the yellow side to this whole blue side, which would be 9.6. So 6 to 9.6, okay? When we cross multiply, I'll save you a little bit of time. 9.6 times 5 is 48. So we get 48 is equal to, now when you cross multiply this way, make sure you distribute. 6 times 5 is 30, and 6 times x is 6x. So this would be 30 plus 6x. And then 6x then would be equal to 18 when we subtract 18 from both sides. So x is equal to 3. Okay, so the directions said to find QP and MP. So now we know what QP is. QP is equal to 3. Okay, so now let's write another proportion to see if we can find, or I guess we don't need to write another proportion. Now we can find MP. Let's see, what's MP? Oh, okay, now that we know that x is equal to 3, if I put 3 here, MP would be 5 plus 3, which is 8. So MP is equal to 8. Now before we take a look at this next example, I need you to look really closely because it's really hard to see. There's a teeny tiny little red arc here and a teeny tiny little red arc there. So I'm just going to make those a little bit more obvious. Okay, so we have, in these two triangles, we have one pair of angles congruent, but also there's a pair of vertical angles, so that gives us 2 pairs of angles congruent. So by angle-angle similarity, that's enough to guarantee that the triangles are congruent. Before we try to write a proportion, though, to solve for x, I think it would be helpful if we wrote a similarity statement. So I'm going to call the triangle on the left, I'm going to call it triangle WSR, and it's going to be similar to, let's see, W has one arc, so I'd start with T. S has no arc, so put V, and then R on the left has 2 arcs, so that would correspond to R on the right. Okay, so I think that's going to help us write our similarity statement. So for example, let's take the ratio of, let's look at WR. What would WR correspond to in the other triangle? Well, W and R are listed first and last, so WR would correspond to TR. So I could take the ratio of x plus 6 to 2x plus 6, so I'm going to write that. X plus 6 to 2x plus 6 is equal to the ratio of, now I took a side of the smaller triangle to the side of the bigger triangle, so I'm going to set that equal to 8 over 10. And again, there would be other correct ways to write this proportion. All right, so now when we cross multiply, remember to distribute. So when we cross multiply this way, we're going to get 10x plus 60. So 10x plus 60 is equal to, when we cross multiply this way, we're going to get 16x plus 48. 16x plus 48. Now there's an x on both sides, so I'm going to subtract 10x from both sides and get 6x is equal to 48. Then, oops, sorry, 60 is equal to, I made a mess of this, 6x plus 48, not equals 48, that's what I meant to write, 6x plus 48. Now I'm going to subtract 48 from both sides and get 6x is equal to 12, so x would be equal to 2. Now let's go back and look what we were asked to find. We're asked to find WR, okay, so when x is 2, 2 plus 6 is 8, so that means WR is equal to 8, and then we need to find RT. So when x is 2, when I put a 2 right here, 2 times 2 is 4, plus 6 is 10, so that means RT is equal to 10. This next example is an example of how we can use similar triangles to solve a difficult problem, or not a difficult problem, but what a problem that would be hard to do in real life. Here we have Hallie is estimating the height of the Cyclone roller coaster in Galveston, Texas. She is 5 feet 3 inches tall and her shadow is 3 feet long. If the length of the shadow of the roller coaster is 34 feet, how tall is the roller coaster? So that's what I meant by something that would be hard to do. It would be hard to get a measuring tape out and measure this giant roller coaster. But what we can do is we can use similar triangles to solve for that, because what we can measure is we can measure the length of the shadow of the roller coaster. It's along the ground, so that would be easy to measure, okay? So what we have here is this is a triangle that represents the height of the triangle, the length of its shadow, and then its hypotenuse. So there's a second triangle. It's kind of hard to see, but it would be a second triangle that would be right here, and I'm just going to redraw it over here. That would be a triangle that's represented by Hallie's height and her shadow, okay? So if we draw a triangle that represents her height and the length of her shadow, now we're assuming that she is standing perpendicular to the ground, so that would be a right triangle, okay? Here's what we know. We know the height of her shadow is 3 feet, and we know that she is 5.25 feet. Remember, 3 inches is a fourth of a foot, so she's 5.25 5.25 feet tall. So these two triangles would be similar. Remember, when they were put together, they share this right angle. And in addition, the same sun is shining on both the roller coaster on Hallie. So we'll talk more about this later. This is called an angle of elevation. These angles would be congruent, so that would be enough to guarantee that the big triangle is congruent to the small triangle. So what we can do now to find what we're missing, what we don't know, is the height of the roller coaster. So let's call the height of the roller coaster X. We don't know that, but we can write a proportion now. We could take the ratio of the height of the roller coaster to the roller coaster shadow and set that equal to Hallie's height to her shadow. All right, so that ratio, that proportion would look like this. Height of the roller coaster to the shadow of the roller coaster is equal to Hallie's height, 5.25, to the shadow of Hallie, which is 3 feet. Okay, so now we can solve that proportion. We would get 3x is equal to, if you took a calculator and multiplied 34 by 5.25, you're going to get 167.5. Then we divide both sides by 3. X turns out to be 59.5. Now, what did x represent? Remember, x represented the height of the roller coaster. We were asked how tall is the roller coaster, so we're done. The roller coaster is 59.5 feet tall. Okay, now if on your notes it says, let me see, if it says homework down here, you can ignore that because we're going to do a worksheet in class. So if you have any questions about the notes, you can ask me in class and I will see you then.